at 7 p.m. in this room. And the 7th of November, the exam duration gonna be 1 hour and a half. It's gonna be 22 questions of 1 hour and a half because chapter 5 has a lot of calculation. So the questions have calculation. So this is why the duration of the exam is more than the first exam. So it's gonna be 1 hour and a half. We're not gonna have a class at the 7th of November at 8 a.m. I'm gonna hold a help session Monday the 5th of November at 6 p.m. in ISB 221, which is in this building. Now, this session is not a review session, it's a help session. So, what does that mean? That means I'm gonna wait on Friday, I'm gonna send you an email, send me the questions that you want me to go over during that session. So let's say you have question 1 in exam 3 for 2012 from the practice exam. You don't know how to solve it or you need some kind of guide how to do that. So you just send me the number of the question and the exam and I put them in slides, and during the help session I'm going to help you do that as a group. The same as now, we're going to do it as a group or as a lecture. But for example, if I get 0 questions, I'm not going to answer, and it's not a review session that I go there and repeat whatever I've been saying before, because you already heard the lecture. It's all about practicing. So from Friday, I'm going to send an email saying, send me all your questions, even if it is a question on OWL that you feel, oh, I don't know how to do that, you can send me an email and we can go over it during that help session. Now, again, if you have a conflict with another exam, contact me as soon as possible. The last day I'm going to hear about it is this Sunday. After that, it's going to be hard to schedule you for a makeup. If you are registered with the Disability Services, with the DS Center, please call them ASAP to schedule for your exam. What's going to be included in the exam? All in Chapter 5, all in Chapter 5, all in Chapter 6, and a small part of Chapter 7. Whatever we're going to go over today and Friday, but not Monday's lecture. Okay? So that's what's going to be included in the exam. Practice exams, you have 3 practice exams, exam 2 from fall and spring, and exam 3 from last spring. Because exam 3 from last spring have some questions that handle chapter 7, that talk about chapter 7. I already sent you which questions you can solve in that exam, which is exam 3, and which ones you can. Both practice exam 2, you can solve everything in exam 2. Okay? The 2 practice exams in exam 2. With that, happy Halloween. Hope you have good plans for tonight or for today to have some fun before the exam. Today we're going to start with chapter 7. So chapter 7, we're going to use all what we learned in chapter 6 to go through chapter 7. So in chapter 7, we're going to learn the electronic configuration, how the electrons reside inside an atom. We talked about shells, subshells, orbitals. Today we're going to talk how the electrons going to fill those orbitals. So what did we learn in chapter 6? So we learned in chapter 6 that L equals 0, that corresponds to an S, and S has 1 orbital. Usually we represent an orbital with a box. Now each orbital can accommodate maximum of 2 electrons. So that tells me that the maximum number of electrons in an S is, so maximum you have 2 electrons. For a P, it has 3 orbitals. We represent them by 3 boxes that are connected to each other. That means they have exactly the same energy. That means the maximum number of electrons that can sit inside a p orbital 6. For D, 5 orbitals. So the maximum of 10 number energy So exactly the same wording. That's for P, this is for D. Okay? And for F, the maximum gonna be 14 electrons because it has 7 orbitals. Therefore, 14 electrons is the maximum. Now, we said before that when we're writing those S, those subshells, S, P, D, that we put a number just prior to, for example, 2S. And we said that this 2 represents the shell, represents N, the principal quantum number. And N represents how close are we to the nucleus. Is it N equal 1, which is the closest, or N equal 2, which is far away from the nucleus compared to N equal 1. Now the number of electrons inside an orbital, we represent that by a subscript up there. For example, let's say I have 1 electron in an S. I'm going to put 1 in there. That tells me there is in shell number 2, in the subshell S, I have 1 electron, or there is 1 electron. So this is what the subscript in here means. This is what this means, and this is what does S mean. Okay? And this is what we're going to do today, is figure out the electronic configuration. Now, as we said, the maximum number of electrons inside an orbital, maximum, we can put maximum of 2 electrons. Now, we learned that in N equal 1, in the shell, in the phase shell, we have only S, which is 1S. In N equal 2, we have 2S and 2P. In 3, we have 3S, 3P, 3D. In 4, we have 4S, 4P, 4D, and 4F. Now, when the electrons, regarding the electrons, where exactly the electrons gonna fill first? Okay, the electrons gonna fill first according to the increasing of NL, N plus L. Okay? So, for example, the N plus L for 1S equal 1. Why? Because N equal 1 and S, the N for S equal to 0. So that's 1. That means the electron gonna fill 1S before 2S. Before, if we use the same rule to see which shell gonna be, which subshell gonna be filled first. So the 1S before the 2S, then 2P, then 3S, then 3P, then 4S, then 3D, and you can keep going according to the N plus L. Okay? So from now on, you need to know that the first shell that's going to be filled, or the first subshell that's going to be, orbital going to be filled is 1S, followed by 2S. In other words, you need to learn both. You need to have this in your mind all the time. 2S, 2P, 3S, 3P, 4S, and then 3D. So this is the way that we fill the electrons in the orbitals, and this is called Aufbau principle, which is according to the N plus 1, N plus L. If 2 subshells have the same N plus L, the subshell of the lower N will be filled first. And whatever we get, the series that I wrote down there, follow those 2 rules, which is we fill them according to the increasing N plus L, and if 2 subshells have the same N plus L, we fill the one with the lowest N first. Okay? So we're gonna use this, you're gonna learn this, keep that in your mind as we're going today through the lecture. Okay. Now let's start with hydrogen. Let's write the electronic configuration of hydrogen. Hydrogen have 1 electron, and I know that the first subshell that I'm gonna fill is 1s, and I have 1 electron, so I'm gonna put it as a subshell. So 1s1 is the electronic configuration of hydrogen. We call this kind of configuration, which we represented as SPDF, we call it, or I will call it SPDF configuration, electronic configuration. There is another way to represent this, which is by box, and we call it the box notation electronic configuration, which is representing the orbital by a box, and each box can maximum contain 2 electrons. For hydrogen, it has only 1 electron, so this is the way that we're going to represent it, 1 electron. And we call this the box notation. Now let's look at the helium. So 1s, first I'm going to fill the 1 as the maximum number of electrons that can be accommodated in S is 2 electrons because each orbital can accommodate maximum of 2. So 2 and helium has 2. So this is the number of electrons. Okay. Now the box notation for this, it says that maximum number of electrons that I can accommodate in an orbital are 2 electrons, but the first principle is Pauli's exclusion principle, that no more than 2 electrons can occupy the same orbital, and if there are 2 electrons, which is the case of the helium, 2 electrons in the same orbital, they must have opposite spin. And we learned that in the last 2 slides of chapter 6, if you remember when I talked that no 2 electrons have the same 4 quantum numbers. So let's talk about the quantum numbers of this electron. First, it is in shell equal 1, so n equal 1. It is in subshell S, that means L equal to 0, ml equal to 0, because the value of ml can be any value from minus L to plus L. Here we don't have a choice but 0. And for this electron, the ms is plus half. For this one, the n equal 1, the L equal to 0, the ml equal to 0, while the ms equal minus half, because the ms represent the spin, and since each one they should have opposite spins to each other, so they would have different ms. So there are no 2 electrons that they have the same 4 quantum number. At least the ms gonna be different. And this is what we call the spin that we talked about, the spin quantum number, that if the electrons are in the same orbital, they're gonna have opposite spins, ms plus half, ms minus half. Okay? So this is the first rule. You need to know the Pauli exclusion principle as you're filling, and even if you're asked, what is the Pauli exclusion principle, or what does that mean, how does that reflect in the electronic configuration, you need to know this, the wording of this principle, which is the first principle of. Now, so this is helium. Again, I'm going to write it one more time because I'm going to use it somewhere in here. Lithium 3, so 1s2. The second subshell that I can fill is 2s. It has 3 electrons, 2 and 1, that's 3 electrons. Now the box notation is going to be 1, 2, 3. Again, I apply Pauli exclusion principle, the maximum of 2 electrons, and they should be opposite. They should have opposite spin. 1 arrow up, 1 arrow down to represent they have opposite spins in there. Now, if we look to the SPDF configuration of lithium, we find that it has the electronic configuration of helium, because 1s2 is the same as the electronic configuration of helium. So this is the third way that we represent configuration, electronic configuration, is by using the noble gas notation. So if I find that the core electron, that the electrons in there, it looks like one of the noble gas, I'm going to put the noble gas, and that tells me this is the electronic configuration of the noble gas, which is helium, followed by 2s1. And usually we do that just to, for this case, it's not a big difference. But for example, when we begin talking about bromine or iodine or potassium, just to minimize how much writing we're gonna do as 1s2, 2s2, 2p6, blah 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 blah. We just put the noble gas and then keep going. Noble gas notation and keep going. So how you gonna know which noble gas you're gonna use? It's always this way. Let's say fluorine. Fluorine, you can use the noble gas notation of the noble gas that is in the row before it. So it's helium, and then you keep going. For chlorine, you use the noble gas notation of neon. That means 10 electrons, and you keep going with the notation till you get the other 7 electrons. And we're gonna talk more about it practically. And for the Br, you use argon, which is 18 electrons, and then you keep going with the notation until you get the 18 electrons. The same as in here, we said helium, it's 2 electrons, and then 2 plus 1, that's 3 electrons. Okay? And we call this the noble gas notation. And this is the box notation. And this is the SPDF notation. All of them are right, it's just writing the same electronic configuration in different ways. Okay, let's go to the beryllium. The beryllium, it is 1s2, 2s2, so 2 plus 2, 4. I'm gonna use Pauli exclusion principle. If I wanna write the noble gas notation, beryllium is in row 2, so I'm gonna use the noble gas before it, which is helium. Helium has 2, and then followed by 2s2. So we're gonna go now to more electronic configuration. Okay. Now, what about boron? So for boron, I'm gonna fill 1s and s2, 2s2, 2p1. So 4, 5, 1, 2, 5, which is the total number of electrons for boron. So this is the SPDF notation, and this is the box notation. I took for the P3 boxes because it has 3 orbitals, so I'm representing those 3 boxes of the P with three boxes there. Now the noble notation, boron belongs to row 2, so this is the helium notation, 2s2, 2p. Okay? Okay, we're going to go to the carbon. So it is 1s2, 2s2, that's total of 4 electrons. 4 plus 2, that's 6. 1, 2, 3, 4, 5, 6, so that's 6. Now let's write the box notation. And P has 3 orbitals. Now, okay, I have more than one choice. Should I put the electrons, both of them, in this orbital? Put them this orbital? Should they have the same spin or opposite spin? What I'm going to do in here? And here comes Hund's rule. Hund's rule states that if we have 2 electrons, if we have the possibility to put them in separate orbitals with parallel spins, that is more stable than putting both of them in the same orbital. And this is why I'm going to put the electrons this way, each one in an orbital without pairing them up. And think about it this way. Let's say you live in a dorm or in an apartment with 3 bedrooms and 1 living room and a kitchen, and you are 3 roommates. I'm sure, for sure, you're not going to all take the same bedroom and live in it, right? You're going to spread all over the apartment, each in his bedroom or her bedroom, until you have a 4th roommate coming in, then you squeeze that person in one of the bedrooms. The same in here. If we put the 2 electrons, let's say I do that, if I put the 2 electrons in the same orbital, they're gonna remember they have the same charge, they're gonna repel each other, and it's not gonna be a stable configuration. This is why this is wrong, this is right. And here comes Hund's rule by statement. And the statement says Hund's rule. When placing electrons in a set of orbitals having the same energy, which is the P3, the 3 orbitals have the same energy, the same for D, the 5 orbitals have the same energy, for F, the 7 orbitals have the same energy, we place them singly as long as possible. As much as you can put them, each one alone, do it. If you need to pair them because you have 4 electrons, then you pair them. So this is also, you're responsible to know what's Hund's rule if you're asked what is Hund's rule. Now, we talked about the helium, we talked about lithium. If we look back to the electronic configuration of lithium, the orbital that have the highest N, which is in this case, this one, which have N equal to, and it has number of electrons in the outermost shell the number of electrons in the outmost shell, which is the one with the highest, and we call those the valence electrons. So if I ask you what are the valence electrons of helium, they are 2 electrons, because it is the number of electrons in the highest n shell or orbital. For example, in this case, n equal to is the highest in here between the two, so this is the outmost shell, and the number of electrons in there in this orbital are called the valence electron. Why are these important? Because n equal to, that tells you that is related to the periodic table. If n equal to, that tells you it's period 2. That means this element is in the second row in the periodic table, and this represents the group. And it's telling you that lithium is in group 1A. If we look to the periodic table, lithium is in the second period, row 2, and group 1A. So from the electronic configuration, you can figure out where exactly is the atom in the periodic table, and it is vice versa. From the periodic table, you can figure out the valence electron. What is the valence electron of the element? Okay, let's take another case, which is the boron. The valence electron are those with the highest n, which is 2. Both of these are the valence electron in this case. So that tells me that boron belongs to period 2 in the periodic table, and it belongs to group, in this case, if we have two orbitals which have the same, the outmost, the highest n, we add the electrons up. That tells me it's also group 3A. If we look to the periodic table, boron is group 3A and in periodic table, which is exactly what the valence electron told us. Now, the electrons that are not the valence electron, anything which is not the valence electron, are called the core electrons. Now, usually the loss and gains of electron, which we're going to learn about in chapter 8, all happens from the valence electron. So when the elements or atoms do bonding, they do that or lose or gain electrons, it's going to be from the valence electron, not from the core electrons. Now, let's go back to the periodic table that I have in here. Both of these, now group 1A, all group 1A, they have the valence electron as ns1. Anything in here have ns1 as long as it is a neutral atom, not, for example, sodium plus or sodium minus, or if it is an atom, it is neutral, its valence electron gonna be ns1. Now the n differs from which period you are. For example, for hydrogen, the valence electron is 1s1. For lithium, because it's in 2, in period 2, it is 2s1. And those only the valence electron. We're talking about the outmost shell, not the whole electronic configuration. But that's going to help you during writing the electronic configuration, because if you know something is in group 3A or 1A, you know for sure that it should end up with S1, NS1. For group 2A, everything in this group is NS2, have a valence electron as NS2, and as you can see, 2s2, 3s2, 4s2, 5s2, it depends on the period. We call these two groups the S group for a good reason, because the valence electron ends with S. In our later on in exams, we're going to ask you, what is the S block element that have this? And we're referring to 1 and 2. Now, let's go to 3A. Everything in 3A, their valence electron, if they are neutral, is ns2, np1. So total 2 plus 1 is 3. Definitely it changes the same way. It depends on the period, what is n. For 4A, it is ns2, np2. So 2 plus 2, 4. This is why it's group 4A. And for this one, ns2, np3. ns2, np4, ns2, np5, and ns2, np6, except helium, because it is an exception for this case. So this is why helium is considered as an S block element, because it ends up with S. Okay? Now we call the yellow ones in here all group from 3A till 8A, we call all of these the P block. for a good reason, because they end up with P. Yeah? Now these ones in here, they are called the transition metals. And they are called the D block, and we're going to talk about it at a certain point today about the D block. Again, they are named D block because they have the D subshell filled. Okay? So this is kind of how we can, from the periodic table, figure out the configuration, or the other way around, how to know if I give you, for example, an electronic configuration without the name of the element. This is one of the Uric laws, although there is another method to figure it out. So what we're going to do now is some eye clickers, just to make sure that you get the idea. Okay, so I'm going to do this first. So sodium 11, so let's say with the noble gas notation. Sodium 11, so sodium belongs to this row. So I'm going to look at the noble gas before it, so it is neon. And I know that neon is going to end up, since it is in the second period of the noble gases, all the noble gases have NS2 and P6. Since it's in 2, that means it is 2,6, 2P6. That means after the 2p, I should fill the 3s. So that corresponds to 10 electrons plus 1 electron, 3s1. Does that make sense? Would you like me to repeat that? Yes? Oh. So if I wanted to write the noble gas notation of any elements in the periodic table, I look at it, then I take the noble gas in the row before it, which is group A. I'm going to put neon, right? So you know that corresponds to 10 electrons, but which orbital you're going to start filling after that? Is it 2s, 2p, 3s, 3p? Then you look to this, you know that, okay, all this group have NS2 and P6, right? As a valence electron, as the outermost shell. We just talked about that. Neon belongs to group 2, to period 2, the noble gas. That means its valence electrons end up with 2s2, 2p6. What comes after 2p to fill? 3s. And this is why I put the 3s. Then I say I have 11 electrons for sodium. 10, this represents this neon between two parentheses represent 10 electrons, because I look to the periodic table and I find that neon has 10 electrons, so I'm left with 1 electron in there. This is how we write the noble notation. It may sound a little bit hard at the beginning, yet it's going to save you a lot of time. So instead of me writing 1s2, 2s2, 2p6, 3s1, I just wrote instead of all of this neon. This is why we teach you how to write it using the noble notation, because it is easier than writing a very long notation out there. Okay? So let's get started with an IQG. So I'm going to stick it at F1.
It's fine. I think this was my favorite. It was really easy. Except when we did it, we made the arrows going straight up and down.
Okay.
I don't like when she does it down. Sloppy.
And check what is. So I have 75% for BB is the right answer. So again, it's group 7A and period 4. So yes, you have, first of all, in this case, it must be 4N. So that's period 4. That's group 7, 5 plus 2, 7. So that looks right. The other doesn't look right because of the of either this reason or another reason. For example, this N equals 3, that's wrong because it's in period 4. This one, it has neon in there, that's wrong because argon is a noble gas before it. Now, so B is the right answer between those 4. Let's do one more. What is the element with valence electron configuration 3s2, 3p2?
Did you have the valence electrons were slowed down? Wish you was telling us this is the period number. So go through and then you add these together to get
Okay, so let's put it up here and see what you think. And I have 79% for A. A is the right answer. So first of all, N equals 3, that means it's telling me it's period 3 of the periodic table. And it is, both of these are N equals 3. That means group 4. Group 4. So I want something in period 3, group 4, that's endos to silicon in there as the element. So this is the kind of exercise that you're going to see on OWL. Either it's asking you to write the electronic configuration or the other way around, which is getting what is the element. It's going to ask you about S block, P block, D block, which we're going to cover sometime today. Okay? Now, if I'm you, okay, I'm going to help you just do some of the electronic configuration. Yet, if I'm you, what I would do, this is the electronic configuration of everything in the periodic table. If I'm you, at least I will sit down and write the electronic configuration of the first 3 periods of group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. If you do, at least try 10 of them. Once you get that you're writing them right, you're ready. That's all what you need to know. That's what we need you to get prepared to. So if I'm you, in addition to the OWL, I'm not gonna grade this, I'm not gonna see this. This is just an advice, take it or leave it. If I'm you, I'll just sit down and try to write the electronic configuration of randomly from the first 3 periods of the periodic table. Now the others are harder, especially when we get to the lanthanides and actinides, which are the 2 ones with 1 star and 2 stars. Those are hard to handle, but the others, you can handle it. Try to write the electronic configuration yourself. That will help you a lot. And since here you have all the electronic configuration, you can go back and check whether you did the electronic configuration right or not. So that's for you to keep. Now what we're going to talk about is the electronic configuration of the transition metal, and I'm going to talk only about period 4 transition metal. That means this. And I'm going to ignore all of this, and the same on OWL, you're not going to see those 3 periods. And I'm doing that because there are a lot of exceptions as we go through the transition metals. and this is, and you'll never see it during your non-major in chemistry. So we're going to talk about the transition metal of period 4. Now, we call that this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Now, these are called the 3B, 4B, 5B, 6B, 7B, 8, 9, 10. Sometimes they are all represented as 8B, 11B, and 12B. So those are called the transition metal. Sometimes, now in here they just change it. Sometimes you would see this as 3, 4, 5, and then they call this 13. So it's different notation to how to use the periodic tables, but the most known in the US. Now the other notation is European, but the most known in the US is 3B, 4B, 5B for the transition metals. Now they are called the D block for good reason, because, and we're going to talk only about this one, because we're going to fill after, it's going to be, there's 3D going to be filled. For S 3D, it's going to be filled. So let's see how we're going to handle the transition metals. So let's say cadmium, which is the first transition metal in period 4. Let's write the electronic configuration of that. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s, okay, 4s2, 3d, 4s2, 3d. Okay, so now I have 10 and 10, those total of 10 electrons, that's 20, and then 1. Now, the first thing that in this case, we're filling the 4s before the 3d according to the chart that we learned about. Do you remember the second slide, where I said we fill 1s before 2s is 3, and 2s before 2p, then 3s, 3p, 4s, 3d. Now, sometimes in OWL, what you're gonna see that they put this electron configuration, they would write it as 3d1, 4s2. So they fill the S before the 3D, yet they put it the other way around. And you have to get used to this notation. It's either or, both of them are right. 4s2, 3d1. So this is how we write the electronic configuration of all of transition metals gonna have 3D fill. Now, the valence electrons in this case, first this is represent the period. So this is period 4 because it's the highest n, so it is period 4. Although it is written before the 3D, it is still in period 4 because the highest n is 4. So it's in period 4, and when we're gonna look to the transition metal, the number of valence electrons are those in 4s and 3d, which is different than what we talked about before. Because in the elements before we said if it is ns2, np2, and n is the same, we add those two numbers of electrons. In this case, the period is 4, 2 plus 1, that's group 3. That since it is D, it tells you it's period 4, group 3B, and it is a transition metal. How did you know it's a transition metal? Because it has a D there. How did you know it's not like a 3A in group 3A? Because it has a D in there. Okay? So this is how we write the electronic configuration of transition metal. Let's think about the noble notation, which is usually the one that you're gonna use for cadmium 21. So I'm gonna look this cadmium. I have argon 18 electrons, represent 18 electrons, 4s2, 3d1. Okay, 18, 19, 20, and 1. Okay? So the same for titanium, we're gonna do it as we're gonna do titanium, vanadium as I click it. Now there are in this period in the transition metal there are two exceptions, and those two exceptions are chromium and copper, and this is why I'm talking about them in here. So let's start writing the electronic configuration of chromium. Write it down. I'm going to give you 1 minute to write down the electronic configuration of chromium. Go ahead, I want everybody to do so. most probably, most of you did that. 4s2, that's 20. 3d4, right? Most of you. Do you agree that this is the electronic configuration of chromium according to what I told you? This is what it is. Guess what? This is wrong. Although according to what we learned, that's right. But this is not the right configuration. Wrong. I'm going to put it in red. That's wrong. Why? Because we have an exception. For chromium, there is an exception. And we're going to write it argon 4s1 3d5. And the reason behind that in this case, 1, 2, 3, 4. So in the case above, you have 4s2, 3d4. So you have 2 electrons in an S. 1, 2, 3, 4, 5. And you have 4 electrons in a D. While those 2 electrons in the 4s, they are in the same orbital and they are repelling each other. So we figured out experimentally that this electron kind of jumps from here to this orbital, to this empty orbital of the D. And this is why the right electronic configuration of chromium is 4s1 3d5. And the reason behind it, because it's a more stable electronic configuration. Because it's half filled, all the orbitals are half filled, and they have no repulsion. While in this case, this s orbital will have repulsion. So more stable electronic configuration. So this is one of the exceptions of the transition metals out there. Now the second exception, so you have to keep that in mind. You're going to be asked about it on OWL in exams. Later on, when you go to Chem 112, you're going to hear about copper, and you need to know that this is the right electronic configuration of chromium. Now let's go to copper. Also, when we do copper, when we do the electronic configuration of copper, it's 4s2. So that's 18, 19, and this is 29. So this is the right electronic configuration of chromium. Again, this is the reason behind it's 4s1 3d10 instead of 4s2 3d9. So usually if we follow the rule that I told you about, you would write this one, argon 4s2 3d9. But this is also not the right electronic configuration of copper, it's an exception. The right electronic configuration of copper is argon 4s1 3d10. The reason behind it here also is that I'm going to have one electron, one unpaired electron in the S, which is more stable electronic configuration than this one in here. So you have to keep in mind that copper and chromium are the 2 exceptions, and you need to know how to write the right electronic configuration of those 2 elements. Okay? So these are the 2 exceptions of the transition. Now what we're gonna do is we're gonna do some eye clickers about the others. All the other transition metals in group 4, they don't have exception except chromium and copper. And I address them here so that you don't get confused after that. So let's start with titanium. What is the electronic configuration of titanium?
Let's see.
And stop it at 120. So I'm gonna stop it right there and check what you think, guys. Very good, 95% C, thank you. That's great. Okay, so titanium 22. I'm gonna look to titanium. The noble gas before it is argon. After argon is gonna be 4s2. That's 18 electrons. How I know that? I look to argon. It has 18 electrons. 18 plus 2. That's 20. After 4s we have a 3d. So this is 20. This is 20. So this is the electronic configuration of titanium. Okay. What is the electronic configuration of chromium? And I'm gonna stop it at 1.
Let's just see how many people are gonna get it wrong. You know.
Okay, so I'm gonna stop it right here and check your answer. Very good, 90% for B, that's right. Because chromium, we just talked about it, it's an exception. So chromium, 24, again, it's argon, 4s1, 3d5, because this is a better electronic configuration or a more stable electronic configuration than 4s2, 3d4. So that's this one. Let me see what's next. Let's do the copper and we'll be done. Stop it at 50.
We just did this one too.
And the right answer is C. Since everybody is about to be. Okay? Again, copper is another exception of the transition method. Okay? So keep that in mind. I'll see you Friday. And happy Halloween.